Alright, this is a quick little introduction for the Calorimeter Lab, and in case you can't tell, lab number 2, I totally shamelessly stole this from my 202 classroom. So what we're going to do is we're going to take a look at energy when there is no phase change, and then we'll take a look at energy when there is a phase change. At the end of the day, energy will always be conserved. Now, you're going to go ahead and make a prediction what happens if you mix equal amounts of 20 degrees and 60 degrees Celsius water. And then we're going to go ahead and we're going to run the experiment and see what happens. So you're going to click on that guy right there. You're going to come to this page. This page right here, we're going to go ahead and click on the Run Experiment tab. And we're going to choose water. And I'm just not going to choose the correct masses or temperatures for you, but you can kind of see how to mess around with these guys. Note that you do have to hit the next button. We can then go ahead and choose water, and again you're going to choose different masses and temperatures, but I'm just kind of showing you what to do. We can then click the next button. I do want you to click these guys because you can see some interesting things, and you're going to mix those guys together. Now what's going to happen is the temperatures are going to change, and they're going to meet in the middle, and you're going to record what that temperature is. So all of that stuff right here is taken care of right here and right here. We record the final temperature right there, and pretty straightforward. We calculate how much the temperature changed by for the hot water and for the cold water. Then what we're going to do is we're going to calculate how much energy was gained and lost. And what we're going to do is we're going to use this equation right here. Q is equal to mc delta T, and what you should see is that this guy right here is going to be negative, this guy right here is going to be positive, but at the end of the day the sums of the Q is going to be equal to 0, which more or less says energy is conserved. It's neither created nor destroyed, as it always should be. The only errors you're going to have is going to be rounding. Then what we're going to do is we're going to choose a solid. We're going to choose copper. We're going to set the mass to 50 grams and the temperature to the boiling point of water. And more or less, we're going to dump that into some cool water. So you're going to choose those guys right there. What we can then do is we can say, well, I can record the temperature just like I did before. How much heat was gained by the cool water? Well, what we can do is we can say the Q of the water is equal to mc delta T, and you're going to get this guy right there. Note that this guy is going to be positive, and this guy right here is going to be negative, whatever that number is. It came from the metal. Then we can say Q is equal to mc delta T, and we can try to solve for the specific heat. That's going to be right here, and of course it's going to be perfect within rounding because, well, simulations are perfect. Note in the real world we lose a little bit of heat to the environment, but it is what it is. Then we're going to take a look at what happens when there is a phase change. So what we can do is we can say when there's a phase change, we have this thing called latent heat. And if we're talking about water, we would be talking about 0 degrees Celsius or 100 degrees Celsius water for the melting or boiling point. We're going to be melting some ice, so now we're talking about 0 degrees Celsius. You're going to just rerun the experiment, and we're going to then go ahead and choose the solid tab, and now we're going to choose some ice. Pretty straightforward. I'll show you how to do that really quickly. You're just going to hit the reset button. We're going to now choose solid, and we're going to scroll down to the very, very, very bottom, and we're going to choose ice. I'll let you set the masses and temperatures and all that good stuff, and I'll hop back to the more enjoyable part. What we can then do is we can record everything as we did before. We can record the final temperature, and we can say, well, how much heat was lost by the water? Pretty straightforward. We can say this is going to be the heat, and we're going to have now the mass of the water, the specific heat of water, and the change in temperature of the water. The heat that was gained by the ice, well, this guy right here is going to be a number. This guy right here is going to be the same number. The heat was lost by the water, so it was gained by the ice. The only thing to be careful of is we have two flavors of heat to worry about when it talks about the ice. We're going to warm up that blob to the final temperature, and then we're going to have the latent heat right here. So what we can do is we can say, well, what was the mass of the melted ice water? Well, that should be the mass of the ice. I mean, we're not changing the number of particles. The temperature of the melted ice water, well, we started off at 0. So what we can do is we can say, let's first calculate the heat that was gained by warming up that blob, and this is going to be the heat of the ice water, and this is going to be the mass of the ice. the ice has changed into water, so it's the specific heat of water, and the change in temperature of that ice water as it goes from 0 degrees Celsius up to the final temperature. So this is kind of this little slice of the pie right there, and you're going to subtract it from this guy right there. What's remaining is going to be the heat that is gained by the melting ice, so we can go ahead and divide that number by the mass and get the latent heat. If you don't get 334 joules per gram, something bad happened, and you should be taking a look, or you should be sending me an email. Pretty straightforward. This is the hardest of the 3 labs for the remaining of the class, and I wish you the best of luck on it.